Hello friends, today I will discuss the derivation for rotating magnetic flux in the three-phase induction motor. So here the major key words to understand this topic are star connected stator, three-phase AC waveform, three-phase AC current, three-phase flux, three-phase rotating magnetic field, Faraday's right hand thumb rule. So let me consider first here how the star connected stator is coupled to the rotor, which is also a star connected winding, and also we see the how the stator winding is connected, and then how to use that connection for analyzing the circuit related to this. So if you look at this, this is the star connected stator winding like this, or YB. These are the three windings, and its shaft is coupled to the rotor like this. This is the rotor. So there is an air gap between the stator and the rotor, and here are the slip rings through which additional resistance can be connected like this. This is also a three-phase rheostat. So when you look at the stator winding or stator, we find like this. This is the stator. On this, we want the three windings like this: R phase, Y phase, B phase. And for each winding, there is a starting winding, there is a ending winding. So starting windings are used to connect the winding in star or delta. In this case, we are going to connect this stator windings in the star connection system. And end connections are utilized for connecting the supply to the stator. So look at this. This is the R phase. This is the starting winding wound on this stator like this. And then that winding goes to the opposite side like this, and then it is wound and it is coming out. Similarly, this is the B phase and this is the starting point. So it will be wound like this, and it goes like this and wound here, and then it comes out like this. Similarly, another winding, that is, it starts here, goes like this, and then comes out of this. So start 1, start 2, start 3 are used to connect the winding in star here, and N1, N2, N3 are connected to the supply. So that we show in a point form like this. This is the stator, and the stator surface have the windings like this. So this is R phase, and this is a return path of the R phase, and this is the B. This is the B return path. This is the Y phase. This is the Y phase return path like this. And this is the three-phase AC waveform that we supply to this stator winding. But for mathematical analysis, so we start the waveform, we take the waveform from here, means we take this as the 0, means our phase starts here, means it becomes a cos waveform, means we write the equations, current waveform equations in terms of cos, so that we can easily solve the or understand the phenomena of rotating magnetic flux. Similarly, B and Y phase also. So once we know this direction of current at the instant, so then we should understand what is called the Faraday's right hand rule. So what right hand thumb rule indicates is, if the current flowing inside the coil like this, then we put these four fingers into the paper and then we curl it, means they come out like this. Then we keep the thumb perpendicular to this curve, then we get the thumb like this in this direction. So this thumb indicates the direction of the magnetic flux produced by the current flowing into this coil. So this we have to keep in mind. See, this is the coil and the current is entering into this. So we keep these fingers into this ring and then we curl them, then they come like this. Then the thumb indicates, which is perpendicular to this curls, will show the direction of magnetic flux or magnetic field produced by the current. So this we are going to utilize for analyzing the circuit here. So as I said, stator windings are connected in star. So as said, starting windings we connect in the star and the end connections we give to the supply. So this is the starting winding of the R phase, this is the starting winding of the B phase, this is the starting winding of the Y phase. We connect all those starting windings together like this to form the star connection. And the end connections are R dash, Y dash, B dash. These three are going to be connected to the three-phase AC supply. So look at this. Once we connect the supply to this three-phase winding on the stator, then as per the Faraday's right hand thumb rule for R phase, so the current enters into the board or paper and here it is coming out. So once we put the right hand fingers into this paper, then the thumb indicates the direction of the flux produced or magnetic flux produced, that is in this direction, that is from left to right. And this flux phi r or phase r flux, we treat this as positive direction of the flux in the R phase. So negative direction means automatically it becomes in the reverse direction. Similarly, for B phase, apply the Faraday's right hand thumb rule. So here current going into the paper, so put the fingers of the right hand into the paper and then curl it, then the thumb indicates the direction of the flux produced by the current flowing in the B phase. So that is, we get like this. And the negative direction of the flux B will become opposite, whereas this is the positive flux direction. So this is also the positive direction of the current waveform. Similarly here this is the positive direction of the R phase current. And similarly, when we apply the Faraday's right hand thumb rule to the Y phase, see this is the Y phase and current entering here, apply the Faraday's right hand thumb rule, that is the finger should go into the paper, curl it, then your thumb indicates this direction, that is the flux produced by the current flowing in the Y phase, and that flux direction we call as positive flux direction and we represent here by phi Y. And the negative direction of the Y phase flux is automatically opposite direction, 180 degrees to this phi Y. So this is the current or this is the input that we are giving to the stator winding. For mathematical purpose we are taking, so the R phase current here means automatically this will be treated as, this will become cos waveform. So Y phase will reach its maximum only at 120 degrees from 0. That is, here it will reach maximum value of current by Y phase. Similarly, B phase reach its maximum value at 240 degrees with respect to the R phase. So that is, here it reaches its maximum value. So keeping this waveform in the mind, we can write this current waveforms equations. So IR means we can write phi m cos theta. So because on x-axis it is theta is nothing but angle. So similarly, Y phase current we can write as Im cos theta minus 120. Similarly, B phase current we can write IB is equal Im cos theta minus 240 degrees. So we can write these current equations like this. IR is equal to Im cos theta, Iy is equal to Im cos theta minus 120, Iy is equal to Im cos theta minus 240 degrees. Then we can show their fluxes, respective flux like this. So this is the positive direction of the R phase flux, and this is the positive direction of the Y phase flux, and this is the positive direction of the B phase flux. And when we want to show the negative direction of the flux, then that also we can show like this. This is the positive direction, this is the negative direction of the R phase flux. Similarly, this is the positive direction of the B phase flux, this is the negative direction of the B phase flux. Similarly, this is the Y phase positive direction, this is the Y phase negative direction flux. So having known all this, we start analyzing, or we apply, or we start calculating what is IR, what is IY at a different angles, 0, 60 degrees, 120 degrees, 240 degrees like this. So for my convenience, I am going to apply here only, I will calculate value of IR, IY and IB. So let us see at theta what is going to happen to the IR value, IY value and IB value. So let me form a table like this. This is theta and this is IR, this is IY, this is IB, and the corresponding fluxes, that is phi R here, phi Y and phi B. So let us say at theta is equal to 0, so what is the value of IR? We have seen in the waveform that it will be maximum. So when theta is equal to 0, it becomes Im cos 0. Cos 0 means 1. So we get IR value maximum. So that is we get here. And we can see here with the waveform that at 0 degrees we are getting IR maximum like this. So similarly, it produces same maximum flux, and that we can see here phi m. At same at theta is equal to 0 degrees, what is IY value? Means Y phase current value. So when theta is equal to 0, we get Im cos of 0 minus 120 degrees. Means cos minus 120 degrees means we get minus half into Im. So Iy value will become minus 1 by 2 into Im. So that is what we have written here. Similarly, at theta is equal to 0, that you can see here, Iy value is minus Im by 2. This is Iy and its value is only in the negative direction, and the value is minus, and that is Im by 2. That is what we have written here. Similarly, Ib. So Ib is equal to Im into cos of, because at theta is equal to 0, so we put 0 minus 240. So cos the minus 240 is nothing but minus half. So we get Ib is equal to minus 1 by 2 Im. So meaning of minus means, so its value is in the negative direction. So this is the y phase, you can see here, and its value is only Im by 2, and that too in the negative direction. So we write here Ib is equal to minus Im by 2, and we find corresponding flux produced in the windings like this. For Iy, the flux produced is minus phi m by 2. For phase B, flux is minus phi m by 2. It is directly proportional to the current. Similarly, let us see what is going to happen to the IR, Iy and Ib at theta is equal to 120 degrees. So at theta is equal to 120 degrees means IR becomes IR into Im into IR is equal to Im cos 120. So cos 120 means again it is minus half. So we get IR value is equal to minus Im by 2. The meaning of this is at 120 degrees, so the R phase flux is negative in the direction, and its magnitude is only half the maximum value of the current. So that is why we write here minus Im by 2. At theta is equal to 120 degrees, for Iy is like this, Im into cos of 120 minus 120. So we get Im cos 0. So cos 0 is 1. So Iy value, that is Y phase current value, is maximum. So we write at 120 degrees Iy value is Im. So it is positive. So automatically that flux also positive. And you can see that in the waveform also. So at 120 degrees, Iy is here and it is in the positive direction and its maximum value. So that is what we can see here. Similarly, for B phase at 120 degrees, that is at same value whatever we used for other phases. So again we write like this, Ib is equal to Im cos of 120 minus 240 degrees. That means we get Ib is equal to Im cos minus 120 degrees. So cos minus 120 means it is nothing but minus half. So we get Ib value is equal to minus 1 by 2 into Im. The meaning of this is Ib value at 120 degrees is negative and its magnitude is only half the maximum current. So that we can see here. Ib means this at 120 degrees. Its value is only half, that is Im by 2, and its direction is negative direction. So that is what we can see here. So corresponding fluxes also we can see here. For R phase current, the current is minus Im by 2, so the flux also minus phi m by 2. For Y phase current, Im here, so the flux is phi m here. For B phase, the current is minus Im by 2 and its corresponding flux is minus phi m by 2. So let us see at 240 degrees what is going to happen. at 240 degrees, when theta is equal to 240, so IR is equal to IM cos 240 degrees. So cos 240 means it is nothing but again minus half into IM. So for IR value will become minus IM by 2, means so its value is half the maximum current and its direction is negative direction. So that is what we can see here. IR value is half at 240 degrees and it is in the negative direction, and its value is only minus IM, simply IM by 2. Similarly, Y phase at 240 degrees, IY is equal to IM cos 240 minus 120 degrees, means we get IY is equal to IM cos 120 degrees. Cos 120 degrees is nothing but minus half. So we can write IY is equal to IM cos IY is equal to minus IM by 2. So that is what we can write here. IY is equal to minus IM by 2. So at 240 degrees, IY means this, its value is negative and its value is half the maximum current. So we write here minus IM by 2. So that is what we have written here for IY. So next, for IB at theta is equal to 40 degrees, so IB is equal to IM cos 240 minus 240, means we get IB is equal to IM cos 0. Cos 0 means 1. So we get IB is equal to IM into 1, means IB value is maximum. So where is IB at 240 degrees? This is the 240 degrees and this is the IB waveform, and it is reaching its maximum value, that is IM. So that we can see in the table also. So at 240 degrees, B phase reaching maximum value. So R phase reaching half the maximum value in the negative direction. Y phase also reaching half the maximum value but in the negative direction. And B phase reaching maximum current in the positive direction. And their corresponding flux are also we can see here. For R phase, it becomes minus phi m by 2. For Y phase, it becomes minus phi m by 2. For B phase, it becomes phi m. These are the individual fluxes produced by the individual phase currents in the stator. But these three individual fluxes do not exist. So the resultant flux only we can see. So to get the resultant flux, we have to add this phi r, phi y and phi b. So at every angle we have to add to get the what is the resultant flux. So that is at 0 degrees, at 120 degrees, at 240 degrees. So let us see at 0 degrees what is going to happen. So the formula for resultant flux is like this. This is the vector sum. Phi resultant is equal to phi r, phi y and phi b. All are in vector condition. So look at this. When theta is equal to 0, phi resultant we can write like this. So we have already seen what is phi r. Phi r is nothing but phi m. And then phi y is nothing but phi m by 2. That we can see in the flux vector diagram. This is the R phase. So reaching its maximum value, this is here. Phi r is equal to phi m. And phi y, positive direction is this, whereas this is the negative direction. And because we are getting for 0 degrees negative, so we take this side. So this is the minus phi m by 2 for Y phase. So remember, this negative direction of the phi y dividing this phi r and phi b by 60 degrees like this, means bisecting. So the angle between Y phase, the B phase and the R phase is 120 degrees. From here to here 120 degrees, whereas this phi m by 2 is bisecting this angle, that is 120 degrees. So we get 160 degrees here. So the angle between phi r and phi y by 2 or phi m by 2 is 60 degrees. And we are trying to get the what is the resultant flux. So we have to get the in phase component of the R phase. So we get phi y by 2 or phi m by 2 cos 60 is the in phase component of the Y phase flux at theta is equal to 0 degrees. So phi m by 2. So we take here only magnitude. So we look at the vector diagram, we resolve the vector. So phi m by 2. So in phase component. So cos 60. Phi m by 2 into cos 60. Similarly, for B phase, we are getting the minus phi m by 2. And where is that minus phi m by 2 for B phase? This is the B phase and this is the negative direction B phase. So this negative direction indicates opposite side, that is phi b by 2 or phi m by 2. This is also bisecting the angle between this R phase and this Y phase. That is, it is making 60 degrees with respect to phi r positive. So to get the resultant flux, we have to take the in phase component of this B B flux, B phase flux. So that is phi m by 2 into cos 60 is nothing but the B phase flux at theta is equal to 0. So we get like this. So once we simplify this, cos 60 means half. So we write phi m plus phi m by 2 into 1 by 2. So we write phi m by 4. So here also phi m by 2 into 1 by 2. So we get phi m by 4. So if we add these three vectors, resultant vector is in the R phase direction, that is like this. And that maximum value or the resultant flux value is 1.5 times the maximum flux of each phase. Similarly, at theta is equal to 120 degrees, we know what is the phi r, what is phi y, what is phi p. So we have to go to the flux vector diagram. So this is the flux vector diagram. This is the positive direction of the flux R phase flux, and this is the positive direction of the Y phase flux. This is the positive direction of the B phase flux. So we have seen at theta is equal to 120 degrees, R phase flux is only phi m by 2. R phase flux is only phi m by 2, and that too in the negative direction. So that is why we write here phi r by 2 means that is also equal to phi m by 2, but in the negative direction. At same 120 degrees, and whereas at theta is equal to 120 degrees, that is same 120 degrees, Y phase flux, so the value is only minus half Im, or its value is in the negative direction. So at theta is equal to 120 degrees, phi y value is positive and maximum value, that is like this. Whereas for phi r, the value is minus phi m by 2, like this in this direction, and phi b value is minus phi m by 2, that is negative direction, like this. So only phi y has the positive direction. So we have to resolve the flux in the positive direction of the y phase. So once we resolve that, we get like this. So phi r value is in this direction. So once we resolve that in the direction of the y, so then we have to write phi r by 2 or phi m by 2 into cos 60. Cos 60 is nothing but half. So we get phi m by 4. This is the in phase component of the r phase flux, that too in phase with the y phase flux. Whereas b phase flux is here. So this also we have to get the in phase component to the phi y. So B phase flux is phi m by 2. So when we take the in phase component to the y phase flux, then we get phi m by 2 into cos 60. So cos 60 means 1 by 2. So phi b by 2, that is equal to phi m by 2 into cos 60. So we get phi m by 4. So R phase flux is phi m by 4, B phase flux is phi m by 4, Y phase flux is maximum phi m. So we have to add all these fluxes vectorially, then we get the resultant flux like this. Let us see once we add this. At 120 degrees, so we have seen how the flux vector diagram appears. So only y phase vector is getting the positive current, maximum current, and whereas the other phase currents are negative, so that too they are half. So once we resolve in the y phase direction, we get the resultant flux like this: phi m by 4 plus phi m plus phi m by 4. So then once we add these three vectors, we get 1.5 times phi m. At theta is equal to 0 degrees, we got the resultant flux 1.5 times the maximum flux. At theta is equal to 120 degrees, again we are getting the flux in the y direction, but the maximum value is 1.5 times the maximum flux. So let us see what is going to happen at theta is equal to 40 degrees. So at theta is equal to 40 degrees, so if you look at this, there is only one waveform which has the maximum, that is B phase, whereas the other fluxes or other flux waveforms or other phase waves have the negative values. So we have seen at theta is equal to 40 degrees, the V phase value is Im, whereas the Iy value is minus Im by 2. Similarly, R phase flux is also minus Im by 2. So having known all these values, once we add them vectorially using the flux vector diagram, we get the resultant flux. So because here B phase is getting the maximum value and positive value, this is the B phase flux, positive direction, and whereas R phase flux is minus phi m by 2, so that is this direction, and the Y phase current is also negative and its value is phi m by 2. that we can show here like this. So we have the Y phase flux and R phase flux in the negative direction, and their value is only phi m by 2 like this. And the B phase has the maximum value. So now to get the resultant flux, so we have to get the in phase component of Y phase and R phase with respect to the this B phase. To get the in phase component of Y phase flux, so we have to take the angle, that is the angle between this flux direction and this direction. So because the angle between this and this is 120 degrees, and the angle between this and this will become only 60 degrees. So in phase component means phi y by 2 into cos 60. So phi y by 2 cos 60 means that we can write phi y in place of phi y as phi m. So we get phi m by 2 into cos 60, because cos 60 is 1 by 2. So we can write as phi m by 2 into 1 by 2, that is nothing but phi m by 4 like this. Similarly, R phase flux is in this direction. Its maximum value is phi m by 2. So that we can write here phi r by 2. So to get the in phase component with respect to the B phase, so we have to multiply this with cos 60. So that is phi r by 2 into cos 60, that is equal to phi m by 2 into cos 60. So phi m by 2 into cos 60 means 1 by 2. So 1 by 2 into phi m by 2. So we get phi m by 4 like this. This is the in phase component of R phase with respect to the B phase flux, and similarly this is the Y phase in phase component of B phase flux. So we have the three fluxes in the same direction, that is B phase, Y phase and R phase. Then we have to add these vectorially. Then we have to find what is the resultant flux. Let us see what is going to happen. So at theta is equal to 40 degrees, from the flux vector diagram, resultant flux will become like this. So phi r is phi m by 2 cos 60, and Y phase is phi m by 2 cos 60, plus B phase is phi m. So once we add this, we get phi m by 4 plus phi m by 4 plus phi m. So we get 1.5 into phi m. So this shows at whatever angle that we take, the resultant flux value is the same, that is 1.5 times the maximum flux of each phase, that is 1.5 phi m here, here, here. Even you take at 20 degrees, 30 degrees, 40 degrees, 50 degrees, 60 degrees, 80 degrees, whatever angle you take, up to 360 degrees, we get the same resultant flux. This means the flux is rotating in one direction with a constant magnetic flux. So that we can see the direction also here. So look at this. R phase is moving like this, then followed by Y phase, then B phase rotating in this direction. Let me summarize once again. So to derive the rotating magnetic flux derivation in the three-phase induction motor, we have seen that there is a stator and rotor, and we have seen here there is a stator, and further there is a winding, and that winding will have the ending and that will have the starting, and we have connected the winding in the star form, and we have given the three-phase AC supply to the stator windings, And for mathematical purpose, we have chosen the waveform as cos, and how we choose that also I explained. And then using that current waveform, we have seen how the current value changes at different angles in three phases. And then we have seen how the flux is produced by these three phases currents. And also we have seen at any instant we have to find out what is the resultant flux, and we have seen what is the maximum flux. And also we have seen how the flux rotates, that resultant flux. And we have seen that resultant flux is always a constant magnitude, that too is equal to 1.5 times the maximum flux in each phase. And also we have seen what is Faraday's right hand thumb rule. And also we have seen what is the positive direction of the current vector diagram and what is the negative current direction of the vectors. And we have seen what is the flux vectors in the positive direction and also negative direction. We have also seen how to get the resultant flux using the flux vectors. And we also saw for RYB phase sequence how the stator flux rotates. So in this case we have seen the flux is rotating in the anti-clockwise direction.